Thank you and good evening, Blackpool. This is the end of everything, and as you can perhaps see from the subtitle, I'm talking about the fate of the Earth and the solar system and the sun, and the fate of the galaxy, and ultimately the fate of the universe. So you could say this talk is really to eternity and beyond. So I'm going to give you a little prologue, and then I'll be talking about the future of the Earth, the solar system, the sun. Then I'll be looking at the far future of what's going to happen to stars and galaxies. And then I'll be looking at the far, 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 far future and thinking about where the universe is heading. And then, to avoid you all being too depressed, I'll have a little an epilogue at the end. So a year or more ago, I told you about how the universe began. I talked about the beginning of everything. And I'm not going to go through that talk again, but I said in the original talk that the universe was made in about 3 minutes or so. It took 3 minutes to generate all the hydrogen, which ultimately led to all of the stars and the galaxies that we see today. So it took 3 minutes to make the universe, but it's going to take a lot longer for the universe to come to an end. And in order not to get totally lost when we start talking about the future, especially the far future, I'm going to use this timeline along the top so we can sort of keep track of where we are in the future. Each small box at the top there represents 10 times further into the future, and I'm thinking in terms of years. And so what I'm really saying is that, for instance, if the red box highlights number 2, 10 to the 2, I'm talking about 100 years into the future, or 1,000 years into the future, or 10,000 or 100,000. 10 to the 6 is 1,000,000 years into the future, and so on. 7, 8, 10 to the 9 is 1,000,000,000 years into the future. 10, 11, 12 is 1,000,000,000,000 years into the future. So that red box is going to be moving along that top timeline so that we can sort of keep track of where we are. Otherwise, it's easy to get lost as to exactly how far into the future we're talking about. And I'd like to acknowledge the work of Adams and Laughlin, who published a paper back in 1997, where they outlined the timescale on which various astrophysical phenomena are likely to occur. And that allowed me to get my slides in order. So I'm not doing this topic by topic. I'm doing this strictly in chronological order of when things are going to happen or are likely to happen. So we're not going to deal with 10 years or 100 years into the future. Let's assume that we get climate change under control. Let's assume we don't have too many wars. Let's think of 1,000 years into the future. We know that the spin of the Earth is slowing down because of the tidal effects of the moon. And at the moment, we add a leap second every once in a while. Usually every few years, we add a leap second into our clocks to take into account the fact that the Earth is slowing down. In 1,000 years, the Earth will have slowed down to the point where we won't be adding leap seconds every few years. We'll be adding leap seconds to our clocks every few weeks to keep our clocks synchronized with the rotation of the Earth. And the slowing of the Earth is going to continue way beyond this point, but this is just the first point at which I said something is going to happen. We know stars are going to change, and in 10,000 years, some stars might have gone supernova. But that's rather fluffy comment because we really don't know when a particular star is going to go supernova. But we do know that in 10,000 years, other things are going to change. For instance, we know that the Earth's axis, it's tilted at 23 degrees to the plane of its orbit, and the axis is pointing to different parts of the sky. You can see that the Earth's axis rotates or precesses, and the cycle is 26,000 years. In other words, it takes 26,000 years for the Earth's axis to point at one part in the sky and then eventually come and point at that same point again. So the Earth's axis, if you like, traces out a big circle on the sky. At the moment, the Earth's axis is pointing towards roughly the star Polaris. It's within a degree of the star Polaris, what we currently call the North Pole star. But in another 10 to 11,000 years, the Earth's precession will point the Earth's pole at a different part of the sky, and the Earth's pole will point approximately towards the star Vega. So we will have a very bright pole star. Some people seem to believe the pole star ought to be the brightest star in the sky. Well, in another 11,000 years, it will be one of the brightest stars, making it very easy for Boy Scouts to point out which way is north. So what's the consequence of the pole star changing? Well, it's nothing too dramatic, but there will be changes. For instance, at the moment, the Earth's axis is pointing towards Polaris, and that means we are nearer to the sun, which occurs in January, in northern winter because of the way the Earth's axis is tilted. But if the Earth's axis tilts the other way and points at a different part of the sky, that means we'll be nearer to the sun during northern summer rather than northern winter. And that means the seasons, rather than being somewhat diluted by the effect of being closer to the sun during winter, when we're closer to the sun during summer, that means the seasons are going to be more exaggerated. So there will be changes to the Earth's climate, regardless of what mankind is doing to the climate. There will be changes because of the way the Earth spins. And changes to the Earth's climate that are the result of either changes to the way the Earth is spinning or changes to the way the Earth is going around the sun, these are collectively called Milankovitch cycles. And I'll come back to that term in just a few more slides. On a time scale of 10 to the 5 now, so we're talking about 100,000 years into the future, the Voyager space probes launched in the 1970s are going to start passing by near stars. So for those of you who remember, back in 1977, Voyagers 1 and 2 were launched in order to explore Jupiter, Saturn, and ultimately Uranus and Neptune as well. So at the top of this particular image, the top left, it shows you that Voyager 1 is heading out of our solar system, and on a timescale of many tens of thousands of years, it's going to pass by the star called Gliese 445. Voyager 2 is actually heading off in a different direction, and that is going to pass close to the star Ross 248. So both of these spacecraft are going to be passing through somebody else's solar system in a few tens of thousands of years. Pioneer 10 and Pioneer 11 are also leaving the solar system. They were actually launched earlier than the Voyagers, but they're traveling more slowly, so they'll actually take somewhat longer to reach stars. Pioneer 10 on the right of this diagram is heading off in the direction of Aldebaran. Pioneer 11 on the other side of the diagram, that's heading off in the direction of the center of the galaxy. Still on a timescale of 100,000 years into the future, we know again that the Earth's climate is going to undergo changes. We can see from the historical record, including the fossil records, that ice ages have come and gone in the past. Generally speaking, ice ages come and go on timescales of order 100,000 years. And we know that the Earth entered a so-called interglacial, in other words, a warm period between ice ages. Earth entered one of these phases relatively recently, which means we can predict with some reasonable accuracy that the Earth is going to go through another ice age in about 100,000 years. This is another manifestation of what we call Milankovitch cycles, in which the Earth's climate depends on the tilt of its axis, how that changes, and how the orbit of the Earth around the Sun, including its eccentricity, changes with time. We are still on a timescale of 100,000 years into the future. All this time, the Earth has been slowing down because the Moon raises tides on the Earth, and that's putting a sort of a brake on the Earth's spin. So in 100,000 years, the idea of leap seconds, remember at the moment, leap seconds are added once every few years, but in 100,000 years or so, leap seconds would be needed to be added to our clocks every day in order to keep the clocks synchronized with the rotation of the Earth. In other words, the Earth would have slowed at this point from 24 hours to approximately 24 hours and 1 second. It would have slowed by 1 second over this time period, and hence we'd have to start adjusting our clocks fairly regularly. Still on a time scale of 100,000 years into the future, we can't predict when stars are going to go supernova, but we are pretty sure that this one is a good candidate for going supernova, possibly first. This is Eta Carina. This is a Hubble Space Telescope image of the Eta Carina neighborhood, and for quite a long time now, perhaps thousands of years, Eta Carina is an unstable star that's been shrugging off its outer atmosphere, its outer layers. It's been doing that for a long time and producing this nebula which is currently surrounding the Eta Carina star itself, which is right in the middle of that particular image. So because this star has been losing enormous amounts of material into the interstellar medium, we think this is getting very close to the end of its life, and perhaps within the next 100,000 years or so, this star could go supernova. It's certainly massive enough to be a supernova candidate, and it appears to be very unstable. It might be beaten to the punch by another one that we've heard of, Betelgeuse. Now, I guess you're all familiar with Betelgeuse. It's in the top left corner of Orion. This is an image of the sky taken by an astrophotographer in Prague. That's an observatory in Prague there. In this particular case, he's taken a picture of the night sky and then artificially enhanced how bright Betelgeuse looks to give an impression of what Betelgeuse might look like if it decides to go supernova. It'll be bright enough not only to completely spoil the constellation of Orion, it would be bright enough to be seen during the day. Betelgeuse is only about 600 or so light years away. That's close enough for it to be spectacular if it goes supernova, but far enough away that it's not going to be too much of a danger. We should be able to survive a supernova at a distance of 600 light years. But there are other things that we do have to worry about. On a similar timescale, it might be that a star like this particular star is called Wolf-Rayet 104. Wolf-Rayet stars are stars which have, again, an enormous sort of atmosphere that appears to have been shrugged off the star itself. And some of these Wolf-Rayet stars have these jets. The mechanism of how these jets are produced is not fully understood, but they can produce very intense gamma-ray bursts. And when this star dies, even though it's 7,000 light years away, 10 times further than Betelgeuse, so you'd think you'd be safe. But if we happen to be lined up with these jets, if we are unfortunate enough to have one of these jets pointing in our direction when the star dies, then the resulting radiation they produce could be more powerful than an equivalent supernova. So the rapid rotation of these stellar systems produces these jets via a mechanism that we don't fully understand, and we just hope that these jets aren't pointing in the direction of the Earth, because if they are, it could be serious. It could, in principle, destroy our biosphere. It could, in principle, destroy life on Earth, even though it's 7,000 light years away, if it happens to be lined up. We don't think it is, so we think we're probably safe, but you can never really tell. We're now moving 1 million years into the future. The Sun, and essentially all the stars in the Milky Way, are all orbiting around the center of the Milky Way in their own independent orbits. And that means every once in a while, by chance, we might happen to drift close to another star which is also orbiting the Milky Way at a similar distance. So when we look at where we are and where neighboring stars are, occasionally neighboring stars will appear to get closer to our Sun and then perhaps drift away again. And by monitoring the positions of stars very accurately using a satellite such as the Gaia satellite, for instance, the Gaia spacecraft, we've determined that some stars are definitely going to get close to the Sun on this timescale of 1 million years into the future. So a star called Gliese 710 is actually going to come close enough that it will actually enter the solar system, in the sense that it will get closer to the Sun than our Oort cloud. The Oort cloud being a large cloud of trillions of icy particles that ultimately give rise to comets. When this star gets that close, it is certainly going to disrupt the Oort cloud, because the Oort cloud is sitting there gravitationally bound to the Sun. Bring in another star, even a relatively small star, it's going to disrupt the Oort cloud, and it's going to send shed loads of comets into the inner solar system. So it's been calculated that the result of this interloper coming into our solar system is going to result in probably naked eye comets seen from Earth, possibly a naked eye comet every month for 1 million years. It's going to be very disruptive to our solar system. But it's interesting to note that for a short while at least, our solar system will actually have 2 suns in it, just like other planets you may have heard of. Still on a timescale of 10 to the 6, 1 million years into the future, you might think this picture of meteor crater is supposed to indicate that we can expect an impact like that every 1 million years. No, that's not quite what I mean here. This picture serves 2 purposes. One, you can appreciate, wow, wasn't it lucky, this impact just missed the visitor center. And secondly, you can say to yourself, well, when you think about craters that formed on the Earth, weathering will destroy old ones. In other words, the wind and the rain, etc., will eventually get rid of any signs of very early impacts. So this might have only been tens of thousands of years old. Things that were millions of years old are unlikely to survive simply because of the weathering in the Earth's atmosphere will destroy signs of craters. So you might say, well, okay, that's obviously going to happen on Earth, but for instance, features that exist on the moon, they're going to be there forever because there's no weathering. Well, that's not strictly true, because on this timescale, for instance, that is Aldrin's footprint on the moon, that is not going to survive, not because of weathering in the sense of weathering on Earth, but the moon is continually being pummeled by a rain of micrometeorites raining down onto the surface, and that's pulverizing the surface, and it will get rid of footprints on a timescale of 1 million years. And if you wait long enough, those micrometeorites will actually destroy all of the Apollo lunar lander, the Apollo equipment, the lunar rover, etc. They will not survive significantly more than millions of years into the future because of this micrometeorite rain. We take for granted that it's not a problem on Earth because our atmosphere protects us. On the moon, it doesn't. So it's a different type of weathering that means that things don't last forever. Yes, the footprints will last a long time, but not forever. We're now moving to 10 to the 7, 10 million years into the future. We said that Pioneer 10 is leaving the solar system, and it will pass through other star systems on timescales of tens of thousands of years. So on a timescale of 10 million years, it will probably have passed through hundreds of solar systems if it isn't already picked up by an alien civilization who then say, what is this strange machine passing through our solar system? If they look on the plaque, they'll get some hint. The plaque tells them who sent it, man and woman, to scale with the probe itself, and on the left is a pulsar map that says we are here, this is us, this is Earth, and at the bottom it indicates we came from the third rock from the sun, and the sun can be identified by the pulsar map. So the plaque on the side of Pioneer 10 tells other civilizations where the probe came from, except that on a timescale of 10 to the 7, on a timescale of 10 million years, the plaque will be unreadable. It'll be pitted, it'll be corroded, because the space between stars, the interstellar medium, is not empty. It's full of tiny particles, micrometeorites if you prefer, or just tiny grains of dust. There aren't that many of them, but if you're traveling for 10 million years, plowing your way through this, you will eventually get lots and lots and lots of hits of these tiny little micrometeorites, and eventually the plaque will not be readable. So if it's not picked up in the first 1,000 solar systems that it goes through, beyond that, if it is picked up, the people who try and read it will not understand where it came from because they won't be able to read the map that's engraved onto the plaque itself. Another factor of 10 into the future, Saturn's rings. What's going to happen to Saturn's rings? Before we answer that, it might be worth asking, well, where did they come from in the first place? Well, we think Saturn's rings may have been formed by, for instance, a moon that was pulverized by collision with another moon, or from a comet or something else, or perhaps a moon that never formed properly. When you look at a moon like that, some people think that maybe Mimas, or something very similar to Mimas, one of the moons of Saturn, was responsible for the ring system. And when you look at Mimas, you might think to yourself,
that's no moon, it's a space station.
Because it does seem to have most of the characteristics of the Death Star there. But simulations have been done to see whether or not it's plausible that if you take a moon and pulverize it, do you end up with a ring system? So this was a simulation carried out where they did precisely that. They took a moon the size of Mimas, forget all the other moons for the time being, pulverize it, and then see what happens to the debris. And this is the simulation that shows what happens to the debris. Notice that after only a few days, you end up with a ring system. So it does seem plausible that ring systems, whether it be Saturn's or Jupiter's or anybody else's, were formed from the pulverization of a moon. But what's interesting is if you follow the individual grains, the individual dust grains here, not only does it not take long for the dust grains to form a ring system because they're all interacting with each other, but also you can calculate that each individual particle isn't in a stable orbit. They are all migrating towards the surface of Saturn. So if you start with what we just had and wait a few million years, you end up with the ring system that we all know and love. But that means the ring system is not going to be there forever because it's changing. And if you wait for a longer period, such as 100 million years, all of the particles in the ring system will eventually migrate inwards and rain down onto the surface of Saturn, and the ring system will all but disappear completely. So for those that like imaging or viewing Saturn, make the most of it. It's only going to be there for another 100 million years. On the same timescale of 100 million years, we may say, well, we can sort of get the idea that Saturn's rings aren't going to be there forever, but what about the rest of the solar system? One thing we often forget is that the solar system is not predictable. We tend to look at an orrery or a clockwork system showing how the planets move around the sun, or a tellurian telling us how the moon goes around the Earth and how the Earth goes around the sun. And when we look at these clockwork systems, we say, well, we can predict what's going to happen in the future, or we can say what did happen in the past. For instance, we can say 2,000 years ago was the Star of Bethlehem this particular conjunction of planets. We can run the clock backwards 2,000 years and we can tell almost exactly where planets were in the sky. But we can't do that 100 million years into the future. On that timescale, the motion of everything in the solar system is effectively chaotic. Not only can we not tell exactly where Jupiter is going to be in 100 million years because we can't calculate it, we don't even know if Jupiter's going to be there in 100 million years. We don't know whether the solar system will contain the same number of planets as it does now. It could be that in a few million years, Jupiter could throw one of the smaller planets out of the solar system. We think that the early planets, the early solar system, didn't look the same as the solar system does now, and in the future it could look very different. We can't make predictions on a system that's chaotic. In much the same way, we can't predict what the weather is going to be 1 month from now. We can predict the weather tomorrow, but we can't do it a month in advance. We can predict planets thousands of years into the future. We can predict eclipses thousands of years into the future, but we can't predict where planets are going to be or what the solar system is going to look like on these sorts of timescales. Thinking beyond the solar system to what's going on in the galaxy, that's a sort of artist's impression of what we think our Milky Way galaxy looks like. That yellow dot is us. That's where the sun is, quite a distance away from the center towards the edge. And it takes the galaxy a few 100 million years to rotate once. But at the moment, you notice that we are in between spiral arms. We're in a relatively low density in terms of how many stars per cubic light year, if you want to think of it that way. We're in a relatively low density part of the galaxy. But it's been calculated that on timescales of 10 to the 8 years, 100 million years into the future, we are quite likely to be inside one of these spiral arms. In other words, we're going to be in a part of the galaxy where there's a lot more stars around us compared to now. At the moment, the nearest star is 4-ish light years away. But when we end up inside one of the spiral arms, we could have a lot of neighbors only a few light years away. What's the consequence of moving from a relatively sparse area of the galaxy to a relatively heavily populated area of the galaxy? Well, there are at least two consequences of having a lot of neighbors. Remember what happened when Gliese 710 came into our solar system? It's going to disrupt the Oort cloud and send loads of comets our way, some of which are going to pulverize the Earth, and some of which are going to be big enough to cause us problems. The same is going to happen if we have a lot of neighbors. We are much more likely to have interactions with some of those neighbors which are going to get a little bit too close and send lots of asteroids and comets our way. And we can see that in the record. If we look at how many species have become extinct as a function of time, we see spikes. Every 100-ish million years or so, you can see the scale here is 500 million years, and we've had quite a few instances of lots of animals suddenly disappearing from the fossil record. We know there have been extinction level events, quite a few, over a period of 500 million years. The most recent one is the one we all know about, at the so-called KT boundary, the boundary of the Cretaceous and the Tertiary eras. That's the one that killed all the dinosaurs. So a very big rock came our way and killed an awful lot of species. We survived, lots of species didn't. So we know from the fossil record this happens regularly, and it's thought to be related to the fact that when we move into a spiral arm, where we're relatively heavily density surrounded by other stars, it's likely that we'll get other rocks coming our way. There's an artist's impression. Of course, we don't know what it actually looks like, but there's an artist's impression of a big rock heading towards Earth. If you look at the left-hand side, it looks like it's heading towards Italy. Okay, well, that's bad news for Italy, but anything that's really big will be bad news for the entire Earth. It won't give local problems, it will give global problems. And species will be exterminated when a large rock hits the Earth. That's inevitable. It's happened before, it's going to happen again. The only unknown is, of all the species exterminated, will one of those species be us? We don't know. We've got a little bit of time to prepare, but of course we can't predict exactly when these things come our way. What's another consequence of being in a part of the Milky Way which is surrounded by lots of neighbors compared to the number of neighbors we have at the moment? Well, one consequence is if we have a lot of neighbors, then it's possible that one of those neighbors could go supernova. At the moment, there aren't any really massive stars close to us. We think the only stars that can go supernova are very massive stars, and at the moment, none of the stars close to us are massive enough to be supernova candidates. They're not going to go supernova at the end of their lives. But if in 100 million years we're surrounded by lots of stars, then maybe one or two of those stars might be massive enough to be supernova candidates, and a close supernova could be a problem. If a supernova exists within 100 light years of Earth, that could be problematic. It could be a danger to Earth. If a star goes supernova within 20 light years of Earth, well, that could, in principle, end all life on Earth. 600 light years to Betelgeuse is sort of safe. 100 is a problem, 20 is a bit in your face, and that could be a severe problem for us. You might say, well, yeah, okay, but that's not very likely. A supernova going off within 100 light years, that's not very likely, is it? Well, it's happened before. If we look at the records, we find that supernova have gone off in the past within 100 light years of Earth, and we can tell because when a supernova goes off, it generates certain isotopes, certain radioactive atoms that don't exist naturally within Earth and the solar system, but do occur, do get generated when a star goes supernova. One of those isotopes is called iron-60, a particular isotope of iron. And iron-60 has been seen in Earth sediments. It can't occur naturally, but it's been seen on Earth, and we deduce that must mean that a star has gone supernova relatively close, sprayed a whole load of iron-60 atoms all over the place, some of which have ended up on Earth and ended up in Earth's sediments. We know it was fairly recent because iron-60 is radioactive, and iron-60 will decay on a timescale of many millions of years into something else. It'll decay into cobalt and then into nickel, which means if you see iron-60 in Earth sediment, given that it changes on a timescale of millions of years, if you see it, it must have arrived recently. It can't have arrived a billion years ago. It can't have been there since the Earth formed. It could only have arrived many millions of years ago because slowly it is changing into something else. So that's how we know that stars relatively close to the Earth have gone supernova in the past. And we are predicting that they will do again in the future on these sorts of timescales. We're back to our old chestnut of the Earth is slowing down. On a timescale of 100 million years, because of tidal friction, because the moon raises tides on the Earth, which put a brake on the Earth, effectively the moon is stealing angular momentum, or spin if you like, from the Earth. It's slowing the Earth down, and the moon is moving further away from the Earth. We can measure that year by year, and the moon is getting 3 centimeters further away from the Earth every year. But when you move 100 million years into the future, there's a substantial increase in the distance from the Earth to the moon. The Earth has slowed down to the point where instead of having a 24-hour day, we now have a 25-hour day. The idea of leap seconds has gone out the window completely. There's no point in adding seconds to try and keep your clock synchronized. At this point, if the day is 25 hours long, you may as well throw out the idea of 24 hours and redefine a day as being 100 hours or something like that, or 100 lots of quarter hour. You can decimalize the day if you really want to. But the moon is now far enough away from the Earth. Not only is the Earth slowing down, but the moon has stolen its angular momentum. The moon is now further away from the Earth, and one of the consequences of the moon being a lot further away from the Earth is it will no longer be possible for the disk of the moon to cover the disk of the sun. At the moment, it just so happens that those two objects, as seen from Earth, the apparent size of the moon and the apparent size of the sun, are such that the moon can cover the sun. And so we get a total eclipse of the sun every once in a while. But on these sorts of timescales, the distance to the moon will be so large it will never be possible for the moon to completely cover the sun. And the best we can hope for would be partial eclipses or annular eclipses, in which case a ring of fire would be visible around the disk of the moon. So on timescales of order a fraction of a billion years, no more total eclipses. So again, for those of you who like eclipse chasing, get in now while it's still possible to see total eclipses. But apart from the fact that we don't get the spectacle of a total eclipse of the sun, another consequence of the moon moving further away from the Earth is a little more serious, rather than just being an inconvenience to astrophotographers. The moon has a stabilizing effect on the tilt of the Earth. The tilt of the Earth is 23.5 degrees, give or take, and it hasn't changed much in recorded history. In other words, we think that the tilt of the Earth has only varied by something like plus or minus 1 degree. The cartoon on the left shows you that the tilt of the Earth is sometimes a little less, sometimes a little more, but you can see it's a tiny variation over many millions, if not billions of years. And that's because the moon's gravity effectively stabilizes that particular tilt. But if the moon gets significantly further away, it's been calculated that if the moon is, let's say, 25% further away from the Earth, then the effect of the moon stabilizing the tilt of the Earth is, as it were, lost. And it will be possible for the tilt of the Earth to change erratically. Rather than 23 degrees, it could go to 0, or 40, or 90, or minus 120. It could do almost anything if the moon isn't there to keep it under control. So in other words, again, we can expect some fairly erratic climates if the tilt of the Earth, which of course dictates the seasons at the moment, if that 23 degrees suddenly starts becoming very erratic. And we think that will happen on this timescale. Voyagers are leaving the solar system, and we said it would take 10 to 100,000 years to pass through a star system, which means on a timescale of 10 to the 9, Voyagers will have passed through thousands, if not tens of thousands, of different solar systems. And it's thought that the 10 to the 9 figure, the 1 billion years into the future, is the length of time that the record that's held on Voyager, the golden disk, will be possible to actually play, in the sense that it's a phonograph, so it's got music, so you can listen to people's voices and listen to music. Why do we think that the Voyager disk is going to last 1 billion years, whereas the Pioneer plaque only lasted 10 million years or so? Well, one of the reasons that this disk is going to last longer on Voyager rather than on Pioneer is because the disk is protected by a cover. There's actually physically a cover, quite thick, on top of the disk, and that's going to take the full force of all of the micrometeorites that it's going to go plowing through for the next billion years. So the good news is the disk is going to last a long time, even if they pass through thousands of solar systems and then a civilization picks it up, they in principle will be able to play the disk. The bad news is the disk is protected by the cover is going to end up corroded and pitted, and it's the cover that's got the instructions of how to play the disk. So it depends on how intelligent you think this civilization is. Will they figure out how to play this disk, even though they're not told? You have to rotate it at this speed and put a stylus in, and then the vibration of the stylus gives you the sound we're talking about. Well, they may or may not be intelligent enough to figure that out for themselves. Still on a timescale of 1 billion or so years into the future, the sun is going to change. It hasn't yet run out of its hydrogen fuel. The sun at the moment is about 4.5 billion years old, and it's probably got another 4.5 billion years ahead of it. It's about middle-aged. But it won't be too long, even before it gets to the end of its life and run out of hydrogen and start to inflate as a red giant. Even before that point, its luminosity will slowly start to increase. Been calculated that the luminosity of the sun will increase by about 10% every billion years for a few billion years. And if you think of how warm the Earth is now, if you imagine we are orbiting a star which is 10% brighter, and then 20% brighter, and then 30% brighter, you can see that the Earth is going to get warmer and warmer and warmer. Eventually, it'll drive the Earth into a greenhouse effect, and the surface of the Earth will reach a relatively balmy 80 Celsius. And sooner or later, the oceans will boil dry. Whether we can survive that, well, it depends how clever we are in terms of, well, are we going to go underground? Are we going to wait it out? Are we going to find somewhere else to live whilst this happens? The sun will swell up into a red giant. The red giant is going to be huge. The calculation tells us that the radius of the red giant phase of the sun will be comparable to the size of the Earth's orbit. So in other words, the surface of the red giant is going to start to get very close to the Earth. And you think, well, maybe that could be a problem. Yeah, okay, that could be a problem for us. But people disagree as to whether the sun will actually engulf the Earth or not. Yes, the sun is probably going to expand until it's the size of the Earth's orbit, but the Earth might not be there anymore, because as the sun goes through its red giant phase, there's a very strong solar wind. A lot of matter is going to be lost from the surface of the sun. So the sun loses mass, so the gravitational pull on the Earth is going to decrease. And we know how that works in terms of orbits. If the gravitational pull decreases, the size of the Earth's orbit will increase. And so it might be possible that the Earth actually survives. If you look at the left-hand side, this cartoon shows what I'm talking about. The sun will get larger and larger, but as it does so, it loses mass, and the Earth actually moves away from the sun. So even though ultimately the sun will engulf where the Earth used to be, it might be, but by the time it does it, the Earth is actually in a new orbit, possibly out as far as Mars. This is not supposed to be to scale, so it might be that Earth of the future might be where Mars is at the present. So we don't know whether the Earth is going to be engulfed by the sun or not. It is possible that the Earth will survive. Once the sun has gone through its red giant phase, it will turn into a white dwarf. A white dwarf has got an awful lot of carbon in its core. We're not sure what form that carbon takes. It might be the carbon in the core of a white dwarf is actually diamond. Who knows? There's speculation about what white dwarfs actually look like. But after assuming the Earth survives the sun going through its red giant phase, the Earth has a second problem to deal with. On a timescale of many billions of years, the Earth is going to lose its magnetic field. The core of the Earth is liquid, so we have a liquid metal dynamo generating a magnetic field. But eventually the core of the Earth is going to cool. The core of the Earth is not kept warm by the sun. The core of the Earth, even 4.5 billion years after it was made, is being kept liquid by the heat of radioactive decay of elements within the core. It's nothing to do with energy coming from the sun. So as long as those radioactive elements are generating heat, the core of the Earth stays molten. But after many billions of years, that radioactive decay will not be enough to keep the core of the Earth molten. The core of the Earth will solidify. As soon as you've got a solid block of iron rather than a liquid metal dynamo, you will lose the magnetic field. And as soon as you lose the magnetic field, you'll be exposed to radiation, including cosmic rays. People have hypothesized maybe this is what happened to Mars. Mars is a smaller planet than the Earth, so although this will happen to the Earth in the future, maybe this is what has happened to Mars in the past. It's smaller, so it would have cooled off faster, and if the liquid core of Mars solidified, Mars would have lost its magnetic field a long time ago, and then radiation from the sun and from cosmic rays would eventually have stripped the atmosphere down to what it is at the moment. So we think the fate of the Earth is similar, not necessarily the same, but similar to the fate of Mars billions of years ago. They say bad luck comes in threes. If the Earth survives the sun going through a red giant phase, if the Earth survives losing its magnetic field and being pummeled by cosmic radiation, there's a third problem. The Andromeda Galaxy is coming hurtling in on a timescale of a few billion years. So the Andromeda Galaxy, at the moment 2.5 million light years away, is moving towards us. And on this timescale of a few billion years, the Andromeda Galaxy is going to basically intersect and pass through the Milky Way. It's unlikely that any two stars are going to collide with each other, but all of the gas and all of the dust in those two galaxies are going to hit each other, and there's going to be an absolute riot of new star formation as these two galaxies pass through each other. It's going to be impossible to see which bits were the old Milky Way and which bits are the Andromeda Galaxy passing through us. After about, 4 billion years or so, most of Andromeda would have passed through the Milky Way, and then they will eventually come to equilibrium and settle down as one huge galaxy. This indicates that we no longer are living inside a spiral galaxy. We're now living in what will probably be an elliptical galaxy, and perhaps you can see and perhaps you can't. There are two bright patches here indicating one is what used to be the core of the Milky Way and one that used to be the core of the Andromeda Galaxy. Both of these galaxies have supermassive black holes in them, and we assume that these two supermassive black holes are going to orbit each other, possibly for a few billion years, before eventually coalescing as one. We're now at 10 to the 11 years into the future, and this saga of the Earth's rotation being robbed by the moon finally comes to an end, because at this point, one day is the same as 1 month. In other words, the length of time it takes the Earth to rotate once on its axis, what we call a day, is the same as the length of time it takes the Moon to do one orbit of the Earth. So 1 day is the same as 1 month. At this point, we have total tidal locking. In other words, the Earth is tidally locked to the Moon. The same face of the Earth always points to the Moon, just like the opposite sense, one face of the Moon at the moment is tidally locked to the Earth, so we always just see one face of the Moon. Eventually, the Moon will always see one face of the Earth. In other words, it will mirror what's been happening to the Moon. So you can imagine if you were on one particular continent on the Earth, the Moon would be static in the sky. It wouldn't rise, it wouldn't set, it would just be there. And if you were on a continent on the other side of the Earth, you would never see the Moon. The Moon would never rise and you would never see it, because only one face of the Earth ever faced towards the Moon. And for those that think that's a Photoshop, no, that's a genuine picture of the Earth and the Moon taken with the Deep Space Climate Observatory. It just looks odd because you don't normally see the far side of the Moon in the same picture as you see the Earth. We finally got our red square to the end of this timeline. It's not the end of the talk, no going home just yet. We are 10 to the 12 years into the future. At this point, all of the galaxies in the local group, the immediate family, if you like, of galaxies around the Milky Way, will merge together. So the center of this diagram is the Milky Way itself, and the Milky Way is surrounded by a lot of smaller satellite galaxies. Eventually, the Milky Way will eat all of these up. Galaxies are cannibals. That's how they grow. That's part of the evolution of galaxies, is they merge together and collide. So eventually, all of these small satellites are going to get eaten up. So not only is the Milky Way going to collide with the Andromeda galaxy, M31, eventually the Triangulum galaxy, M33, is going to join in as well, and all of the galaxies in this diagram within a few million light years of the Milky Way will merge together in one giant galaxy. It's not actually, according to that icon, it's not actually going to be a spiral galaxy. It's probably going to end up as a large elliptical galaxy. But effectively, we'll no longer have the identity of individual objects. They will all merge together. But beyond that, I've told you in an earlier talk that it is currently already possible, if you wish, to image galaxies that are receding from us because of the expansion of the universe. We know the Hubble constant tells us the more distant an object is, the faster it's receding from us. At the moment, it's already possible to image galaxies that are receding from us at, for instance, twice the speed of light. I've told you how that was done a few years back during a COVID lockdown. But eventually there will come a time when, if we look at more distant galaxies, there's a Hubble deep field. Here we're looking at mainly galaxies in the far distance. There's a couple of stars in this image. Those stars are part of the Milky Way galaxy. Everything else in the image are more distant galaxies. But there will come a time, because of the expansion of the universe, where all of these galaxies are receding from us simply too fast to image. And so if we were to build ourselves a Hubble Space Telescope in the future, this is what we would see. We would not see all of those galaxies. We would just see the stars that are part of our own Milky Way. And it's sobering to realize that if a civilization comes along in 10 to the 12 years' time, when the universe has continued to expand, even if they built themselves a Hubble Space Telescope, even if they built themselves a fantastic telescope, if they look out into the universe to see what's out there, they would see nothing other than the stars in their own galaxy. A civilization that comes along in 10 to the 12 years of time, 10 to the 12 years into the future, would come to the conclusion that the universe is just the stars and planets within their own galaxy. They would not be aware of the fact that the universe is actually full of trillions of other galaxies, because eventually they'll be simply too far apart to ever image. I said in the beginning of everything that it took approximately 3 minutes to make all of the hydrogen in the universe. And ever since, for the last 13.8 billion years, the universe has been converting that hydrogen by making stars and galaxies. But after a trillion years, or a few trillion years at this point of the timeline, when we're that far into the future, the hydrogen is running out. There's only a finite amount of it in any given volume of the universe, as far as we can tell. So it was all made very quickly, in 3 minutes, but it's not going to last forever. After a few trillion years, the hydrogen is running out. Now, just as an aside, some people think, well, maybe you can make stars out of something else. Is it possible to make stars out of heavier elements? Do you really need to start with hydrogen? A lot of people say, yes, you have to start with the lightest element. Some people say, well, maybe you can start with something heavier. Is it possible to make stars from a greater proportion of heavy elements? Some people have hypothesized that you might be able to make a star and have nuclear reactions occurring with heavy elements, even though the surface temperature of that star is very low. At the moment, we know that it's possible to make a red giant with a surface temperature of, let's say, 3,000 Kelvin. Some people have said maybe you can make stars out of different elements and have a surface temperature which is 10 times lower. Instead of 3,000 Kelvin, maybe you could make something with 300 Kelvin. Maybe you could make something as cold as the ice point. In other words, a star with nuclear reactions at the core, but the surface of the star would be cold enough for ice to form. That's quite a thought. So-called frozen stars. And when I say frozen stars, I'm not talking about the Disney version of Frozen. So if that's the picture you've got in your head, let it go, because what I'm talking about is stars where nuclear reactions are occurring at the core, but the surface is cold enough for ice to form. This is entirely hypothetical. We don't know if that's actually possible. Most people think it can't happen. You need hydrogen. But in order to figure out what happens next, we have to ask ourselves, well, what is the universe doing in terms of this? Well, it's expanding at the moment, but what's going to happen for the future? Well, at the moment, here's a diagram of time on the horizontal axis. So the Big Bang is on the left, now is where it says now, and the vertical axis is how big is the universe. We don't worry about units, it's just how big is it compared to now. So we look at now and say the universe is size 1, and it's going to get bigger, and in the past it was smaller. So we can see that the Big Bang happened. The 4 different colored lines are possible scenarios for what the universe has been doing and will be doing. So the Big Bang, you can see, happened at a time which depends on which particular cosmological model we think is correct. Each of these colored lines corresponds to a different amount of stuff in the universe. How much matter is actually out there? How much energy is out there? If there's a huge amount of matter out there, we would expect an expanding universe to eventually stop expanding because gravity will pull on all of that matter and pull it all back again. And so the orange line shows an expanding universe which eventually gets smaller again and results in a big crunch. That's if there's a lot of matter in the universe. But we don't think there is. We've tried to measure how much matter is in the universe, and we think we're not on the orange line. As best we can tell, we think we're on the red line. In other words, it is possible to make reasonable estimates of how much matter is out there by counting stars and counting galaxies and accounting for all the dust and the dark matter and the dark energy. And we think the universe is expanding according to the red line. We can't be absolutely sure, but that's what we think. So if you look at the left-hand side, the red line hits the axis 13.8 billion years ago. So that gives us the age of the universe, 13.8 billion years. But notice the expansion of the universe there. It's expanding and expanding and expanding. The red line never comes back down again. Not only that, but the red line, the gradient, is getting larger and larger and larger. It's not only getting bigger, it's accelerating. The expansion of the universe appears to be accelerating. We don't fully understand what's going on, but the red line is our best guess as to what the universe is doing. So I'm going to ignore the possibility that the universe is going to collapse into a big crunch and assume the universe goes on expanding. And in order to make sense of this, because I've got a 10 o'clock train to catch, we're going to change the numbers at the top here. So instead of each box being 10 times further into the future, each box is now 1,000,000 times further into the future. So in other words, 10 to the power 30 is some ridiculous number, a zillion years into the future. I don't even know what numbers we should give to this. 10 to the 48, gazillion years. I don't know what we would call 10 to the 66. We're just going to rely on the numbers rather than try and label how many zillions we're talking about. Where did we leave this argument before we took this little aside as to what the universe is doing? Let's assume the universe just continues to expand. We said it takes 3 minutes to make all the hydrogen, but after a few trillion years, the hydrogen runs out. Stars can live for an awful long time. Stars can live for trillions of years, unlike our sun, which only has a sort of 10 billion year lifetime. Small stars might live for trillions of years, but they don't live forever. So if the hydrogen has run out, what does that mean? There will come a time when there are no more stars. The age of starlight will come to an end. The fuel won't last forever. The stars themselves, when they're dead, well, they'll continue to orbit just as they did before. They're the same mass, they're just not shining because they've run out of fuel. So dead stars are left orbiting the galaxy like zombies. There will be white dwarfs, there will be neutron stars, there will be black holes, none of which are shining by the process of nuclear reactions at the core, producing energy, which then results in starlight. White dwarfs, well, it seems a bit odd to call them dark, but white dwarfs will go dark because a white dwarf is just the core of a star after it's shrugged off its outer atmosphere, like the sun, for instance. And white dwarfs will cool down. There are no nuclear reactions to keep them warm. So they will start off quite warm, but they will cool off. Given long enough, they will become black dwarfs. In other words, they're just basically lumps of carbon. Stars, some stars might be ejected from the galaxy. A lot of them will simply be swallowed up by the supermassive black hole that's sitting at the core of what we believe is every galaxy in the observable universe. So supermassive black holes will eat all of the stars that are left at that point. We believe that there are magnetic fields at the center of every galaxy. This particular galaxy has been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the telescope in the back end of a 747. It's now been decommissioned. If anybody wants a 747, I think it'll be on eBay now if you want to go check it out. So that's been decommissioned, but that, before it finished, mapped out the magnetic field lines in the center of the galaxy, center of another galaxy, NGC 1097, and it's believed that matter is funneled into the supermassive black hole at the center of the galaxy by the matter following these magnetic field lines. What happens next is, again, a little bit uncertain. On a timescale of 10 to the power 36, silly money in terms of how far into the future we're talking, but we know that at the moment atoms are made of a nucleus with protons and neutrons surrounded by a whole load of electrons. What we don't know is what's going to happen to the protons. Protons are the charged particles that are part of every atomic nucleus. Some people believe that protons might decay, they might change, in which case every atom in the universe will fall to pieces. But we don't know whether protons will decay or not, and if they do decay, we've got no idea of the time scale on which they'll do that. We know it's no less than this number. They're not going to decay any sooner than 10 to the 36-ish years, but it might take them a little longer. They might never decay. But basically, there will come a time when there are no more atoms. Even assuming protons don't decay, then atoms won't survive forever, because even black dwarfs will evaporate and there'll be no atoms left. There are no atoms in neutron stars, there are no atoms in black holes. If those are the only objects left, then there are no atoms in the universe. Black holes will continue to crash into each other every now and again. The black hole at the center of our galaxy is millions of solar masses. The black hole in the middle of the Sombrero galaxy is billions of solar masses. Eventually, these black holes are going to collide with each other and they're going to merge together and make absolute monsters that could be trillions of solar masses in mass. But they are not going to last forever. Even black holes don't last forever. They evaporate. It's a very slow process, which is why this red square is getting a long way over to the right-hand side. You have to go to ridiculous timescales to see black holes evaporating. So why do they evaporate? Well, the simplest explanation is to say, well, quantum mechanics, the rules of physics that tell us how small particles behave, small things behave, tell us that it is possible to borrow things from nothing. Maybe that's how the universe came to be in the first place. You can borrow from nothing and make a particle and an antiparticle, which then annihilate and pay back the energy you just borrowed. You can borrow energy, make stuff, the stuff then annihilates and gives you the energy back again. It's like taking a loan from a bank, but eventually you have to repay the loan. Some people say, well, that happens all the time according to the rules of quantum mechanics. Maybe that explains how the universe came into being in the first place. But how does that help us understand this business of black holes evaporate? Well, Hawking said, well, what would happen if you make a particle and an antiparticle right outside a black hole? So let's imagine the event horizon of a black hole. What if you make a particle and an antiparticle and whoops, the black hole eats one of them but not the other? Now you can't get the annihilation to pay back that energy. It looks like a particle has just come out of the black hole. That's not actually what's happened, but it behaves in that way. It looks like there's radiation coming from just outside the event horizon. That's now become known as Hawking radiation because Hawking first proposed that. Now it just so happens that when you calculate how much radiation you would get from a black hole, you find that the radiation increases with decreasing mass. In other words, large black holes don't radiate very fast, small ones radiate very quickly. So if you watch a black hole evaporate, it evaporates very slowly while it's large and gets smaller and smaller and smaller, but as it gets smaller and smaller and smaller, it radiates faster and faster and faster, so you get this sort of avalanche effect, and it finally disappears in a flash of radiation. Even the most massive ones, we know that small black holes will evaporate quickly, but even the big monsters will evaporate eventually, as long as you've got the patience to watch. It'll take much, 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 much longer for supermassive black holes to evaporate compared to black holes that are the mass of our sun, for instance. But look where the red square is now. We're at 10 to the power 84, and the largest black holes are now starting to evaporate. So how far do we actually need to go to the end of time? Well, time perhaps doesn't have an ending. But if you go to 10 to the power 100, 10 to the power 100 is Google. Not that Google. That is a misspelling of that. That was the intention. It is said that the original Google was supposed to be OL, but somebody misspelt it and it ended up as LE. 10 to the power 100 is a Google. And we reckon that after a Google years, the last black hole would have evaporated. That means there's nothing interesting left. There's just a little bit of radiation floating around the universe. In other words, from this point onwards, nothing happens. There is no matter left. There's no atoms, there's no matter. There's just photons of radiation kicking around the universe. And as the universe continues to expand, that radiation gets more and more and more dilute. known as the heat death of the universe. So if nothing happens, the concept of time becomes pretty meaningless. If nothing is happening, then the concept of time passing doesn't really have a great deal of meaning. And to remind us just how silly 10 to the power 100 years is, let's just write it out. I don't normally do this, but that's what we're talking about. We're not talking about billions or trillions or quadrillions of years into the future. We're talking about a silly time into the future. But you can do the calculations, and that's what the physics tells us, that the universe will effectively come to an end after that sort of length of time. Eternity is a very long time, especially towards the end. That's a Woody Allen quote from a long time ago. It's difficult to put everything in perspective, but I liked the quote from XKCD, for those of you who like the online comic. They said, to put it into a human perspective, a human is simply a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email quite a lot. That's one way of putting humans on the cosmic scale, as it were. But yes, I don't want people to be too depressed about what's going to happen in a Google years, so let me just finish with an epilogue. We live in a golden age. The sun is middle-aged and stable. It's nicely well behaved. The moon is at just the right distance, not only to stabilize the Earth's axis and hence stabilize the seasons, it's also at the right distance to give us the spectacle of a total eclipse of the sun. And thanks to evolution, mankind is able to explore and discover and understand the universe around us. We can visit our closest neighbors in the solar system, and we can build ourselves spacecraft and telescopes that allow us to see galaxies that are billions of light years away, and we can see a huge observable universe. But we couldn't have done it a long time ago. Humankind could have not have arisen in the very early universe because we needed generations of big stars to generate all the heavy elements that we need for life as we know it. So mankind could not have existed in the very early universe. And we've just seen that in the future, the universe is very dark and very boring. So the best time to exist is now. Thank you for listening.